we were interested. Okay. Okay. Can you see it now? Yes, we are. Right. Let's suppose that we are interested in a little hypothesis. And this hypothesis is that Scots people are taller than English people. Right. So, for whatever reason, I've decided that I believe Scottish people are taller than English. And so we've got to figure out how we could test that. It's called the hypothesis, right? A hypothesis is a statement that you are putting forward as the truth, but hasn't been proved yet, right? So a hypothesis could be right, a hypothesis could be wrong. And so we're going to test this one. I believe Scottish people are taller than English. And so what I do is I collect some data on the English. And I found out that the average height of an Englishman is 65 inches. So my hypothesis now becomes the average height of a Scotsman is greater than 65 inches. So far so good, right? Now we'll assume that that's true, right? That somehow or other somebody did a census and they got that. So what I'm going to do is I went out and I did a nice simple random sample of 1,000 Scotsmen. And we found that their average height was 66 inches. And that the standard deviation was 4 inches. And we want to find out whether or not we can prove that Scottish people are bigger than that. Okay. So we are going to use SALT. And we are going to get a confidence interval. What kind of size confidence interval should I do? And that's really up to the person who's the scientist. So if you were the scientist, do you want a 90, a 95, a 99? Let's give you three choices. A 95, a 90, or a 99. Which of those do you want to use to create our confidence interval? You want a 95. Any particular reason, or it just is as good as any of the others? Robert?
It was like the best fit.
Yes, okay. Spit in the middle, right? Now, 95% confidence interval. It is. So what I'm now going to do is I'm going to nip over to WebAssign, if I can get the buttons to work, and go here, and go here. And I'm going to hit the use salt button. And I'll bring this guy over here. And I'm picking inferential statistics. You want to know what heading I'm using. And it's a one sample T. I'm doing this one for safety, right? I don't know if the distribution is normal. I'm pretty sure 1,000 is big. So I'm going to use a one sample T. And the mean that I got was 66. And the standard deviation that I had was 4. And that my sample size was 1,000. You're comfortable about where you put the numbers in to create your confidence interval, right? So one sample T, right? So if you're doing a mean, right, a confidence interval of a mean, and you're doing it with a sample, always use a T distribution to be safe, right? Just play safe, pick that one. Now, confidence interval, and 95% is already there. So I'll generate the results. And I get that the confidence interval was 65.8 up to 66.2. Right, so let's go back and see what that looks like. Now, we are 95% sure that the average height of Scotsman is in this range. Great. Now, in this story, we've added an extra little piece. Is the average height of a Scotsman likely to be bigger than 65? Would you agree that every single number in that interval is at least 65 or bigger? Oh, here we go again. All clear. We're good. So, would you agree every number in that interval is greater than 65? And because of that, I can now say that I have shown or proved that Scots people are on average taller than the English. And I'm basing it on the fact that the average height of Scotsmen is somewhere in this range. And no matter what number in this range it ends up being, they're all bigger than the English average of 65. See that? So that would then enter, you know, the kind of the body of knowledge that Scots people are typically taller than English, or whatever it should be, right? This next story, okay, I know. Darn it. Go away. Right. Let's do the next one as a medical example. Let's suppose we would like to do, you know, one of those when you get a blood test, they have a kind of normal range, and then we want to know what kind of numbers are outside of that range, right? For example. So let's pretend that we're interested in finding the usual range for potassium. So you want to tell doctors what's the typical range of potassium levels for adult females, right? Because very often you have to do it separately for females and males, because in body chemistry, they're not always the same, right? Certain things are just different. Women's bodies, men's bodies, different, you know, hormones and whatever, right? So you have different values. So this is the range of potassium for adult women. So what we're going to do here is we collect a sample of, let's say, 200 women. And we measure their potassium level. And since I have no idea what potassium level is, can we pretend that the average was 37 from my sample of 200, right? And that the standard deviation was 5. And so we're going to do a range, a normal range, that's maybe wrong, almost a bad word, a typical range, how about that, for what the potassium level for a woman should be. Now that means that we have to decide on a 90, a 95, a 99. Couldn't we even do a 68%, which I typically hate, but in this case, wouldn't 68% be the middle 2/3, right, kind of thing, right? So what level do you want? What confidence interval shall I create from this data? Give me a number. There's no wrong answer to this. Just what number do you want?
68.
68. So we're going to do a 68% confidence interval. All the numbers that we need are kind of here, right? And so SALT pretty much takes care of a lot of the groundwork for us, which is great because it means we don't need to worry about it. Right. Are you looking at the same page that we were a minute ago? Right. So I'm going to change the mean now, and it's now a 37. And we're going to do a standard deviation of 5, and the sample size was 200. Because that sample size is 200, wouldn't you expect a bigger range of values, right? A bigger width, which is typical. We're going to turn this down and we're going to do a 68. And I'll generate the results. And the results that we have are, I'll do it to one decimal place, 36.6 to 37.4. And let's see how that might be interpreted then. So what you might do is just on a magazine, you know, not so much a magazine, but a medical journal, you know, the Lancet or whatever, they might say, right, the updated potassium level, the typical range is 36.6 to 37.4. So if you get a person and that's where it is, that's very normal. That's kind of typical for a woman, right? Nothing going on here. Of course, wouldn't you call anybody bigger than that? You would say that person has a high potassium level. And so if somebody had 40 or 45 or 50, wouldn't you call that a high potassium level now? On the other side, if you got numbers down here, wouldn't you say that person had a low potassium level? And don't different diseases, you know, generate high and low potassium or anything else? So what you've really got here is, haven't you collected data that allows you to actually be used? Right, where does it, you know, if I get it all the time, I get once a month blood tests, they suck more blood out of me than they should. And I get these things and they tell me, you know, normal range, normal range, and then I have a couple, I always have a couple, this is too high or that is too low. And that's where it's coming from. Now, I'm not saying it's a 68. Couldn't they do maybe a 90 or whatever number they've decided on? But once you've decided on what kind of confidence interval, you could consider that the normal range, right? The typical range. Anything bigger is high, anything on the other side is low. Has anybody ever had a blood test with that kind of thing going on? Yeah. When you look at them, Lauren, don't they give you a range of what's okay and then they tell you where you are, or do they just tell you where you are?
I get them from my A1C, so I get a range of where I'm supposed to be for my age, and
So it
then
would be
a
that one?
secondary range of where like everybody else is.
Right.
Some of that, yes.
Right. So if you've ever wondered where this data comes from, do you now realize what they just did is they just collected a lot of data? Now, the chances are that it is even bigger than 200. Can you imagine that they've probably collected a lot more than 200 blood samples, you know, in America? So they would have really, really good data on what's a typical range of values, right? And so you would look at that in a much wider kind of degree of accuracy. Am I selling you the fact that this process can be actually useful? Yeah, you can use it for anything, right? You can use it to tell if Scotsmen are taller than English. You can use it to find normal, typical ranges of any blood chemistry thing that you're looking for. So for the last, got to tell you this because it just came into my head and you know what I'm like. I had a really cool disease. I had a pituitary gland tumor. So inside my brain, I had a tumor that was on my pituitary gland and it was growing. And I never knew I had it because there are two versions of it. Well, there's three. One is cancerous, which I didn't have. And the two versions that are left, one is an active tumor and one is an inactive tumor. And an inactive tumor, which is one I had, doesn't produce any chemicals. You know, your pituitary gland produces various hormones and body chemicals, right? It's actually the one that, do you know some people who have the growth version one? It produces too much growth hormone and you end up with people 11 feet tall. Most of them had that disease. They had the pituitary gland tumor, but the tumor was producing excess amount of growth hormone. Sometimes they produce X amount of testosterone. And so women who get that can sometimes have beards and have very masculine features because of that. I mean, so it's a pretty nasty tumor if it's one of them. So I got the best of the three. I got the one that didn't produce any hormones or anything and just basically grew. And that's why I never knew I had it because I had no symptoms. And I was on holiday with my wife in Scotland, and I thought I needed a new prescription because I wasn't seeing so well. And my wife doesn't drive in Scotland, so I was driving, and we did a great tour. We toured all over England, and had a great time. And so I went to the local place in Scotland and got my eyes tested. I thought I need a new pair of glasses, and they gave me a test, and they gave me a peripheral vision test, and the woman didn't like the answer, and she thought, you want to come back tomorrow and we'll just do it again, because I think, you know, these results aren't very normal. And essentially what was happening is the entire outside was becoming blind. Right. And so if it kept on going, my eyesight would have shrunk to the point where I was blind. Actually, I would have died before then because the tumor would have probably grown into my brain. And it was a fascinating, it's a great story. It's fascinating. And so I went to the guy, and it got double checked in America. And the minute he saw the results, he said, yep, yeah, this isn't good. And they did a CT scan and they found it, and that was great. And then I had to go and get an operation. And the cool thing is, if I'd had the same thing 10 to 15 years ago, I would have been dead, because the success rate for the operation was horrible, because what they used to do is cut off the top of your head and pop it out so they could get into the tumor. And you can imagine that didn't end well for a lot of people. But technology had moved on, and what they do is fascinating. They stuck a hole right through my nose and another one through my palate, and they did that keyhole surgery thing. And one of them was a little camera so the guy could see what he was doing, my brain surgeon guy. And the other one was a little thing with a kind of suction spinny thing on it. And they basically just shaved my tumor to nothing and sucked it through the tube. And then they kind of plugged up the holes. And that was fascinating. I can prove that I have a brain now, because I have brain scans to make sure it doesn't come back. And so I do have pictures. So it's kind of, I'm totally free. I had it 10 years ago, and they gave me a brain scan every year for 5 years, and nothing had came back. And then they've moved it to every 2 years. And then I think I'll have another one next year. And then if that one's clear, they move it to every 5 years, and I'll probably be dead before it grows back anyway, so it won't matter. So that was a useful, weird piece of information, but it has made me think of life in a totally different way, which basically means you should always enjoy things as much as you can, because you don't know what's going to happen to you tomorrow. So let's do one more of these. I'm trying to think of a good one to finish with. Try to think of something different. Anybody got an idea? I'm running short of single things, and you can tell me numbers or I can make them up, whatever. Okay. Since nobody can, Lauren, you look like you might be thinking. You got something for me? Whatever you come up with is going to be a sample of 150, because I've decided, and it's going to have a mean, and it's going to have a standard deviation. Okay, I've thought of one. We all know that the typical IQ is 100, but I have a theory that American football players aren't too bright. I have a theory that the average IQ of an American football player is less than 100, because of all that banging that they do to their brain, right? So I went out there and I found 150 American football players, and I gave them an IQ, and they got 99.2, and the standard deviation was 4. And we are going to find out if there's enough evidence in this sample to prove that the average IQ of football players is less than 100? Right, gut feeling. Do you think I'm going to be able to prove it with this data, or do you think that 99.2 is too close to 100 to really be important? What's your gut feeling?
I think it's going to be a little too close to call.
As good as answers any, I don't know, is the short answer. It's very hard to tell when you look at raw data where you're going to go. That's why you have to trust the data. But I am going to do something. I am going to go a 99% confidence interval. So see if I do get evidence, isn't that take it to the bank kind of proof? Because won't I only be wrong 1% of the time, right? So for our last question of today, we are going to take this data and we are going to find out whether football players are not as clever as the rest of the general population. So it was 99.2. Gotcha. And the standard deviation was 4. And the sample size was a bit in the small side, so that's 150. And I'm going to go for a 99%. And we'll generate the result. And the answer we got is 99.2 up to 98.3. So let's zoom over to the other side and see what that looks like. Is that interval enough evidence to prove that football players, on average, their IQ is less than 100? Agreed? On all of those numbers, and I guess I should have done it the other way around. Oh, darn it. It's 98.3 to 100.1. Now, if that had been the right interval, which is not, this is the right interval. Somehow I managed to scan the wrong place. Is that enough evidence to prove that the average IQ of football players is less than 100? What do you think? Are all those numbers less than 100? If I phrase it that way, does it help? Are every single one of these numbers less than 100? No. That means there's not enough evidence. Right, show you what the range might be. If it was a 99.2 to a 99.8, wouldn't that be evidence that their IQs are less than 100? Great, because every single number is less than 100. In a different world, maybe I screwed up totally, and it was 101.1 to 103.7. Wouldn't that actually be evidence that their IQs were more than 100? And if you got the one that we actually did get, and I'm not quite sure what happened there when I hit the buttons, which is that one, since 100 is in the interval, and it doesn't matter that it's almost there, right? It almost got in, right? It almost kicked over. It's still in it, and that means not enough evidence. Isn't that very similar to when you do proportions? That means the first guy's bigger than the second. The first guy's less than the second. And then you don't know. Remember when we did proportions, if everybody was positive, the first thing was bigger than the second, right? The first thing was less than the second, or you can't tell the difference. So although these are proportions and these are means, don't the intervals tell similar stories? You can look at an interval and you can make a conclusion depending on the context. In this case, it's IQs. What that is telling me is this. That interval is telling me that. And this interval is saying, look, I don't know. There's not enough evidence to tell if there is a difference. And when you say, although actually you don't need to say, because everybody's getting attendance today, so thank you for turning up, those who